Thank you, Marielle, and hello, everyone, and welcome again. I'm really thrilled to have so many of you online with us today. For those who I haven't met before, my name is Caitlin Moggle. I'm a research scientist at University of Washington's Puget Sound Institute, and I led this project in collaboration with Kevin, Stefano, Marielle, and Wendell. And today we're going to share with you the results of a Puget Sound Partnership funded project where we evaluated the distribution of risk to marine vegetation in Puget Sound. The overarching goal of this project was to perform a spatially explicit cumulative risk assessment of the current and future threats to eelgrass and canopy kelp, two of Puget Sound's foundational nearshore habitats. We wanted to use this risk assessment to identify risk hotspots, evaluate the relative importance of individual threats to cumulative risk, and produce relevant outputs and tools, including a web tool that we'll explore at the end of the presentation today, in order to inform marine vegetation conservation, restoration, and monitoring at a Puget Sound-wide scale. There are two foundational documents that underpin this work. The first of which is the Thom et al. Report from 2011 that identified stressors to eelgrass in Puget Sound and built the conceptual model that you're seeing on the screen here. In this report, they also had a group of experts rate several characteristics of each of those stressors to produce scores describing the relative importance and our level of knowledge of each stressor. The second foundational document was a paper by Hollersmith et al. In 2021, where experts produced a conceptual model of the drivers and pressures believed to be impacting bull kelp in the Salish Sea. Although this paper did perform a literature review similar to the Thom et al. Report to determine the level of support for each of the links shown here in their conceptual model, they did not produce the expert ratings of kind of stressor characteristics that the Thom et al. Report had done. So one of the first outcomes of our project was to perform a similar rating exercise to the Thom et al. Paper for the kelp pressures. So for this portion, Wendell Raymond at WDFW and I brought together a group of 6 kelp experts to rate the pressures identified in the Hollersmith et al. Paper. And the report from this rating exercise came out in April of last year. But some folks may not have had a chance to see that yet, or may not have seen our various presentations at kind of work groups and conferences. So I'm going to hand it over to Wendell now to discuss more about that part of the project. Take it away, Wendell.
Great. Thanks, Caitlin. Hello, everyone. I'm Wendell Raymond. I'm a research ecologist with WDFW in the habitat program focusing on nearshore habitats and species. So next slide, Caitlin. So to provide these expert ratings for kelp, we took the stressors, or what the Hollersmith authors called pressures, at those list of stressors, and wanted to provide an expert rating and sort of severity and certainty value for each one of those. And as we convened this working group, we made quite a few decisions on how exactly we wanted to do this. And a big one was to do this rating exercise for a couple different subsets of taxa and life stages. This project that Caitlin's going to go through is focused on eelgrass and bull kelp, but we recognized an opportunity we have this group of people together to get some more information. So we focused this exercise on bull kelp, Nereocystis, giant kelp macrocystis, then understory species, and for each of those taxa, the adult or sporophyte phase, and gametophytes for the juvenile life stage. Next slide. So we then rated severity, sort of like how bad is the stressor, and certainty, how much do we know about it, under 6 characteristics. And this is following the similar process done for eelgrass. These characteristics are magnitude. This is the effect of the stressor on a small area of kelp. Spatial extent is the relative amount of kelp habitat that's affected by the stressor in the study area. Timing, that's the duration or sort of biological or seasonal timing that the kelp habitat is affected by the stressor. So is this like kind of a one-off type of stressor or something that occurs year-round, or is maybe only part of the year or something like that? Then reversibility, this is the degree to which the stressor could be sort of removed from the environment, agnostic to cost or sort of political likelihood or feasibility. Then trend over time, this was a very generalized, like, how is the stressor kind of trending? Is it getting worse? Is it staying the same? Is it getting better? And then we also included depth extent, which was something different compared to eelgrass, where we considered like where in the water column is the stressor occurring? Is it close to the bottom? Is it close to the surface? Or is it both of those? Next slide. All right, so then our actual rating used a simple low, medium, high categorical rating with 1, 2, 3 numerical values assigned. There was also a very low category given for our certainty ratings, and then also unknown received a rating of 0. And so if you've been sort of doing the math in your head of how many things we actually rated, it's 720 unique cells in a spreadsheet for our panelists to fill out. So, next slide. All right, so how did we compile all these ratings? So we, after we defined what we were doing and the steps for everyone to take, each member of our panel filled out the 720 cell spreadsheet themselves, sort of rating and rating and certainty scores. Those were then returned to Caitlin and I. We compiled them together, computed means and standard deviations, computed this metric we call total stress, which we'll talk about in a minute. We then, as a group, we had an in-person discussion where we reviewed all our individual ratings and kind of how that all looked, with the primary goal of building consensus and finding places where the panel may have disagreed or interpreted the task slightly differently. We then had an opportunity to edit those ratings, each of the panelists, and then those final values were returned, and we sort of produced the final results from that, which we'll talk about now. So next slide. Okay, so as you can imagine, a 720 cell data set is really data rich, and there's a lot of different ways to sort of dive into the data, which in our report and a forthcoming manuscript that will be available for for anyone to sort of look into what stressor or taxa or life stage you're really interested in. So for today, I'm going to focus on this metric, which we call total stress, which is just the mean of the magnitude, reversibility, timing, and spatial extent stressor characteristics. So in the next series of slides, there's going to be this biplot with rating, sort of the how bad is it metric on the y-axis, and then certainty, the like how much do we know about it on the x-axis. And then each of the points will represent a stressor and what life stage taxa we're talking about. So next slide. And so in this biplot mode, we can roughly divide it into 4 quadrants, where the upper right-hand corner, these are things that are bad and we know it. the upper left these are things that are maybe bad, but we don't know a lot about. And then moving down the lower left, these are things that are maybe not so bad, but we're also not so sure. And then finally, in the lower right, things that are not so bad, and we sort of feel confident that they're not so bad. Okay, next slide. So here's the mean total stress scores, stress and rating scores, or sorry, rating and certainty scores for all 10 stressors and all taxa life stage combinations. So lots of tiny points on the plot, but we're gonna go through the patterns together next. So next slide. Okay, so starting in the things that are bad and we know. The clear result here is temperature, probably not a surprise to most of you. We know that temperature can have pretty negative effects on macrocystis and nereocystis sporophytes. So that's that collection of gray points, both the adult and juvenile stages. Next slide. The next that's kind of on the line is low nutrients, again for macrocystis and nereocystis sporophytes, but a little bit lower on the rating, stressor rating, and a little bit lower on certainty. Next slide. Okay, moving on to the bad and we're not so sure area of the plot. This is dominated by the gametophyte life stage. So this is indicated by the open symbols for multiple stressors. So this includes substrate, algal competition, salinity, mechanical damage, water clarity, and some others. And next slide. And then finally, this so not so bad, but we're not so sure area of the plot. A lot of different stressors with both the gametophyte and sporophyte life stage. So contaminants, epiphytes, water clarity, and both high and low nutrients. And then finally, that last quadrant, the not so bad, and we're pretty sure about it, nothing really falls out in that part of the plot. And I just want to remind everyone that these all of these stressors are still considered by the experts in the Hollersmith paper and all the literature they reviewed to have some level of negative effect on kelp. So just because a stressor maybe plots out sort of lower on the rating doesn't mean that we shouldn't sort of worry about it or be aware of it. And let's go to the next slide. So to kind of wrap up this part of the project and the results from this sort of threat rating exercise, like I said, this is a really rich data set, and I just really showed kind of one perspective of those data today. And that detailed level of data is out there for anyone to dig into. So we think that there's a lot of potential applications for both research and management and restoration to use these data to kind of dig into a stressor or a taxa of your interest and see how the values sort of play out. You may have noticed that rating and certainty are often positively correlated. This is something that our panel picked up on pretty early on in the process, and we immediately wondered, like, the things that we know more about we think are more bad, and it's kind of hard to control for that. But hopefully, with more research and more time, that sort of pattern can be identified. Some more clarity. The panel also really struggled to deal with interactive effects and how to quantify them. We directed the panel to consider stressors in isolation as much as possible, but this was challenging. We all know that these stressors occur in the real world all together at the same time, and especially for things like temperature and nutrients and salinity, those are all fluctuating sort of in concert with each other. So that was a big challenge for this work. our reversibility scores may be the most direct or at least simplest way to point to management or restoration priorities. This is our measure of like how hard does the expert panel think it is to sort of remove this stressor or to mitigate it. Another pattern that we discovered as we thought more about these data is that certainty, like a high level of certainty, doesn't necessarily mean actionability. So temperature is a really good example. We have a high level of certainty that temperature is bad for kelp, but it could be really hard to manage temperature, especially on a large scale. Clearly, research on the gametophyte life stage, so the juvenile life stage, and understory species is needed. That's sort of universally, our level of certainty is lower for gametophytes and or understory species. And like I mentioned, there's a manuscript that the panel is working on that we hope to submit in the coming months that goes into some more detail on the applications of this work and the data itself. So that's all I have. We can have a pause for any questions directly related to this part of the project, but then Caitlin will carry on with the other parts of the work.
And so please feel free to raise your hand when we'll unmute you to ask a question, or you can drop a question into the chat, whichever is most comfortable. Yeah, go ahead.
Hey, thanks. So you mentioned that the panel got together and kind of discussed some of the scoring. Can you talk a little bit more about that? Maybe which ones were decided, oh, this score is too low and that score is too high? And did you come up with like averages, or was it more of a consensus base?
Yeah, good question. It was a great conversation. And a really good example of how that discussion helped us sort of frame the project moving forward is that in the Hollersmith paper, they just identify nutrients as a stressor. And that's how we originally presented it to the panel. But that created a lot of confusion and questions among the panelists of like, well, what do we mean nutrients? Do we mean high levels of nutrients or low levels of nutrients? Because those are kind of different things and could be stressful in different ways. So like, what do we all mean? And that eventually led to like, well, let's split nutrients. Let's make two nutrient stressors. Let's have a high nutrient stressor and a low nutrient stressor. So that's sort of one example. While we wanted to build consensus around the ratings, we also wanted to capture the variability in opinion around a certain, stressor or taxa or characteristic, whatever it may be. So we sort of used the initial set of data to like highlight things where it's like, hey, the panel had a really wide range of opinions here. Like, let's first just take a pause and like make sure, did we all understand this, interpret this the same way? And oftentimes there was some difference in interpretation that we then clarified, which then helped sort of tighten up the scores. But in some cases, the interpretation was pretty, sort of everyone was on the same page, but there was just people had differences of opinion, which is totally fine. And so we now within our final scores, if you dug into the real data, like scores that sort of have a high standard deviation are indicative of where was I don't want to say disagreement among the panel, just like differences of sort of opinion on how sort of bad or certain we are about a stressor.
Great. Thank you for that context, Wendell. And yeah, it was cool to be in the room and see the discussion and evolution before people went back and kind of finalized their scores there too. There was just a double checking and clarification on definitions. When you're talking about the certainty rating, is that measuring the certainty to measuring the stressor, or in terms of the badness of the stressor?
Oh yeah, good question. So certainty is is a sort of a subjective measure of sort of how certain are we in our sort of scientific understanding of the effects of the stressor on sort of the taxa life stage that we're talking about. So the individual panelist made a decision based off of their knowledge and experience and literature of sort of how much do we know about this. So it's not about how certain we are about measuring it sort of in the field. It's like how strong is the body of knowledge about this stressor.
Great, thank you. And our next question is just whether stressors were considered as high or low values relative to the median on impact.
Ooh, can you say that one again?
And Alan, if you want to unmute and maybe elaborate on that.
That was partly,
that
was partially answered on the nutrient question, but it brought to mind you can stress in two different directions given the habitat that the plant is found in.
Yeah, so because of the nutrient splitting, then yes, there was a moment in the panel where we're like, wait, now do we need to have two directions for all of these? And we thought about that for a minute. And we decided to just do it for nutrients because we felt that a high or low nutrient state is a natural state of the environment that could occur sort of to any sort of individual kelp out in the world.
I'm thinking salinity might be one.
Yeah, and so salinity, yes, is another one that we're still having some internal discussions about. And that is more, there's some like semantics of like when we say the stress of salinity is high, is that really indicative of actual low salinity, like low PPT salinity? And that is the basic understanding, but we recognized that we could have confused ourselves when we were working on this. But yes, like for salinity, a high stress salinity is really an in situ low salinity measure.
Good question, Alan. And as Wendell said, part of ongoing discussion. So clearly you've hit in on something well. There's another question here about just elaborating on the certainty rating and that it appears almost everything falls into the low certainty and how the panel then reliably scored mitigation potential when overall certainty is low.
Yeah, good question. So we did not, that's a really good question. I now want to look at in detail how the certainty scores line up with the reversibility metric. And that is something I have not looked at closely. And so to interpret the certainty scores on reversibility, a high certainty score on the reversibility metric would suggest that the sort of the literature or this current body of knowledge is strong, that this that the stressor in question could be removed. Again, independent of cost or sort of political will. But that's a really good question, and I know that's that's a part of the data sheet I want to zoom in on. Yeah, thanks.
Yeah, I appreciate the good questions that prompt follow on. That's part of the value in sharing things here with you all. Any other questions? Again, feel free to raise hand or drop into the chat. Otherwise, we can kind of shift into talking about some of the other preliminary results. Okay, I think let's take it away.
Thank you, Wendell, for sharing those results, and thank you all for your questions. As Mario said, it's really good to kind of gut check our interpretation and our assumptions, and that helps us build out a more complete story around these results. So shifting back to the heart of this project, which was the risk assessment, and just a little bit of background on risk assessment. So cumulative risk assessment is a widely used approach. It was derived originally from fisheries vulnerability assessments, and the purpose is to systematically and adaptively evaluate threats across scales to a focal habitat or species. A recent example here that's fairly relevant. So McMahon et al. In 2022 used a risk assessment for seagrass around the continent of Australia. In general, outputs of habitat risk assessments can be used to identify areas of the greatest relative risk of degradation. And in the case of this Australian study, identifying kind of the southeast region of Australia as being a particularly high risk subregion. And risk assessments can also help to identify the possible causes of risk within those regions and among different scenarios, such as current versus future, or between different management alternatives. And in the case of this McMahon paper, they evaluated the relative change in risk to seagrass resulting from two common strategies that are often proposed for conserving seagrass habitat. One being reducing nutrient pollution and the other being reducing sediment pollution. And in general, understanding the location and intensity of cumulative impacts on critical habitats is an essential component of ecosystem recovery and has been found when performed at scales relevant to decision-making to significantly improve recovery outcomes. In our risk assessment, we incorporated two dimensions of information to calculate risk. So risk was defined as the combination of exposure, which is the degree to which a habitat experiences a threat, and consequence, which is the sensitivity of the habitat to the effects of a threat. And there are several criteria which underlie these two dimensions of risk, and some of which were derived from the expert scores in the Thom et al. Report for eelgrass and the Raymond et al. Report for kelp. And I'll talk about a bit more about the incorporation of the expert scores into the risk assessment later. But just at a high level, exposure was defined, or the criteria that were incorporated into exposure were the geographic overlap between a threat and a habitat, the intensity of the threat in that location, if it is known, and the temporal extent of that threat. And that came from the expert scores. And then for consequence, there were three criteria underlying that. One was the kind of magnitude or severity rating, the reversibility rating, and the trend into the future rating, all of which were derived from the expert scores. So the tool that we use to perform the risk assessment is part of the INVEST suite of tools from the Natural Capital Project. And this tool was called the Habitat Risk Assessment Model. In this tool, you provide spatial data layers describing the locations of the habitats of interest, spatial data layers describing the threats to those habitats, and the information about the exposure and consequence criteria and scores. The InVEST tool takes that information and overlays the spatial data for the habitats and the threats and calculates the risk from each threat to each habitat. And then the risk from each threat is then summed to the total or cumulative risk. And you can evaluate risk pixel by pixel, but you can also summarize risk to larger subregions of interest. Here's the complete list of the spatial data that we synthesized to describe threats to eelgrass and kelp in Puget Sound for the risk assessment. So there are 17 total threat layers here, and these represent what we think are some of the predominant threats impacting marine vegetation in Puget Sound. And in some cases, these layers may actually be proxies for one or multiple pressures or stressors. Some of these are point locations, some are modeled outputs, some are derived from observational data. And in the case of continuous data, either modeled or observational, they were binned into quartiles and then assigned low, medium, and high exposure scores. And next I'll show you some of the maps of the threat input layers that we synthesized. So here are half of those threat layers. We have the locations of seaports in the upper left here. We have the locations of commercial shellfish harvest sites, the locations of shoreline armor, and the locations of oil and gas facilities. On the bottom, we have the locations of dredged material disposal sites. We have continuous data describing vessel traffic intensity, and this comes from observations of AIS transponders that the US Coast Guard collects. And then the bottom right here are impervious surface coverage of the watersheds and percent industrial land use. And in this case, we defined our watersheds and calculated those information about percent impervious surface and percent industrial land use. But then the actual location of the threat in the InVEST threat layer is associated with a buffered point around the mouth of that watershed. So where the stream or the river enters Puget Sound, we put a point there and then buffered that. And the size of the buffers here in these impervious surface and industrial land use layers was the size of the buffer was scaled based on the magnitude of flow coming out of that river or stream. Here are 8 more of the threat layers. The 4 on the left here are again kind of buffered points around river mouths or wastewater treatment plant outfalls. The upper left is riverine influence. This is basically the magnitude of flow coming from rivers or streams. A riverine pulse metric, which describes something about kind of the flashiness or variability of that flow. We had a layer describing riverine nutrient loads. So what are the terrestrial sources of nutrients? What's the relative magnitude of that? And then, like I said, the relative magnitude of wastewater treatment plant outfalls, and specifically their nutrient loads. And then the 4 on the right here are modeled outputs for water quality variables. We have temperature, salinity, low nutrients, and high nutrients. And these all come from a 2014 year run of the Salish Sea model, which is a biogeochemical model of Puget Sound and the greater Salish Sea. But we have trimmed the results here just to be within our study area. And so these describe those oceanographic and kind of biogeochemical conditions as modeled by the Salish Sea model. We also ran a separate version of the habitat risk assessment model, which I'm not going to dig into as much today. But we wanted to represent future conditions as well. And so the changes that we made for the future habitat risk assessment model were that we replaced the 2014 Salish Sea model data with a 2095 future projection run that was from a paper, Kangankar et al., 2019. And then we also, in the future habitat risk assessment model, we added an additional layer, which was sea level rise projections from the climate impacts group. So there was one more step that to kind of get from the expert ratings that Wendell talked about for kelp and that we had from the Thom et al. Report for eelgrass to the scores that Invest would use to assign to those different threat layers. So we had these lists of eelgrass stressors and kelp pressures, and we had the expert scores associated with them. But we needed to match that with the 16 or 17 threat layers that I just described. So which of these stressors are associated with those threat layers? And to do this kind of matching exercise, we surveyed 20 regional marine vegetation experts, so kelp and eelgrass people. Some people responded just about kelp, some responded about eelgrass, some responded about both. And these individuals were asked to indicate which of the kelp or eelgrass stressors or pressures on the left-hand side here were associated with the threat layers that we had compiled for the Invest habitat risk assessment. And if at least half of the experts responded that there was an association between a pressure, and then in this case, the kelp pressures and the Invest threat layer, then we retained the scores for that pressure and associated them with the Invest threat layer. So if at least 50% said yes, then those boxes are in red, and the responses were compiled kind of additively. So we summed the total expert scores for all of the pressures associated with each threat layer. And then the additive scores were divided into thirds for each criterion. This was for timing, magnitude, reversibility, and trend. And these were some of our exposure and consequence scores in the Invest model. So the lowest third of those additive threat scores received an Invest score of 1. The middle third received a 2, and the upper third received a 3. So it's a bit convoluted, but the purpose of this was to capture the fact that, for example, a threat layer describing riverine influence, or essentially the flow magnitude coming out of the mouths of the rivers and streams, would have potentially multiple stressors or pressures associated with that. There could be stress associated with salinity. There could be stress associated with substrate change due to high sediment loads. The river might be warmer, so there could be temperature stress associated with that, etc. So we try to capture that kind of additive effect that might be present with some of these threat layers. So this is what the Invest output looks like. Here is total risk for kelp on the left and eelgrass on the right. And the purple, blue colors are no risk or low risk. Green is medium risk, and yellow is high risk. So at a high level, you can see that risk is spatially distributed around Puget Sound, that there are differences in different regions, and there are also differences in the different taxa, so between kelp and eelgrass. And there are some regions that have maybe a larger grouping of those yellow high risk cells, and there are other regions where there's more low blue cells or green medium risk cells. As I mentioned earlier, you can also summarize risk by subregions, and we did just that. So we used the floating kelp bed indicator subregions that are shown on the left figure here, and then compared total risk from our risk assessment to the monitoring status and trends from the vital sign indicators for both canopy kelp and eelgrass. So we divided the risk results up into subregions that align with the kelp indicator, and then we compared that to the subbasin status or the monitoring status and trends. So this plot shows the values of total risk to kelp from each of the pixels in those subregions. And the subregions along the horizontal axis here are ordered from highest risk to lowest risk. The letters A, B, and C above the bars indicate statistically significant differences between the groupings. And the colors of the bars relate to the monitoring status from the vital sign indicator. So red are indicators considered to be declining based on monitoring data. Yellow are subregions of concern, and green are stable. And then blue are those where we have insufficient data to be able to determine a trend. And for kelp, at least, we see good alignment between our estimation of risk and the monitoring status. So regions that are declining or of concern generally had higher risk compared to regions that are stable. For eelgrass, however, we did not find a good of alignment between risk and monitoring status and trend. So the stable areas and those in green had higher risk compared to the 2 areas of concern, which happened to have lower risk. In general, we found that risk differs by marine vegetation taxa and by subregion. For kelp, the highest risk areas were South Puget Sound and Central Puget Sound, and the Saratoga and Whidbey basins. For eelgrass, the highest risk areas were Hood Canal and North Puget Sound. And for both eelgrass and kelp, the lowest risk subregion was the San Juan Islands. But you'll notice that there are multiple high risk outliers in the San Juan Islands, which could help to explain why this subregion is of concern for both eelgrass and kelp, regardless of low risk on average. Thinking more about the kind of mismatched alignment between our estimation of risk and the monitoring status for eelgrass, there's several possible explanations for this, and we're still kind of thinking about why this might be. So feel free to add your ideas as well. But it's possible that we are missing some important eelgrass threats, that they're just not captured by our data set. Or in addition, the threat data sets that we have compiled, maybe they're getting at the right stressors, but the data sets that we have don't adequately capture the conditions that are being experienced by eelgrass beds. And in both cases, this is challenging, I think, for eelgrass because they're shallower and more near shore, that there may be additional things going on in those very shallow near shore areas that we're just not capturing in the threat data sets that we have been able to compile. And we're targeting data sets that were available across the study area, so capturing the full Puget Sound. So that limited some of the kind of maybe more fine scale or more near shore data sets that do exist, but that don't have the complete spatial coverage we were looking for. And then another possible explanation is that eelgrass status for the vital signs is characterized slightly differently from kelp, and they also technically use different subbasin definitions than the ones that we've used here. So there could just be some mismatch there as well. Another way of that we can evaluate these threats is to look at the relative contribution of each threat layer to total risk. So this is the proportion of risk contributed from each of the threat layers divided by taxa. So eelgrass is on the left and kelp is on the right. And then by subregion within those two taxa along the bottom. The yellows here indicate a fairly low contribution of that threat layer, and the purple kind of almost black color indicates a high contribution of that threat. And again, there were differences between marine vegetation taxa and subregions, and there's really a lot of information that can be gleaned from this figure, but I'll just highlight a few examples. So shoreline armor, for example, contributed more on average to risk for eelgrass compared to kelp, kind of across the board, but particularly in San Juan Islands, where we see a very high level of contribution of shoreline armor to total risk. Another example is that for kelp, impervious surface coverage and industrial land use seem to contribute more to risk overall in South Puget Sound and the Saratoga and Whidbey basins compared to elsewhere. In addition to differences, there were also commonalities. And one of the ways we looked at this was to rank the threats from highest to lowest contribution by subregion, and then kind of look at which data sets seem to rise to the top within each subregion or for each taxa. And what we found was that for eelgrass, shoreline armor, river flow, industrial land use, and impervious surface coverage were commonly in the top 5 threats to eelgrass for each subregion. So these may be kind of universally common threats across our study region. For kelp, nutrients, vessel traffic, industrial land use, and impervious surface coverage were commonly in the top 5 for each region for kelp. You may be wondering, as I did, how the expert scores influenced our calculation of risk. So in addition to running the model with the expert scores, which are the ones outlined in red, these are the results that you've already seen and that we've been talking about. I also ran a version where all of the threats were assigned the same exposure and consequence scores. So I'm calling those the equal versions of the model, and they're outlined in blue here. And at a high level, you can see that the use of expert scores did change the resulting risk landscape. For example, in kind of the Eastern Strait region for kelp, there's in the equal scores version of the model, this long stretch of coastline throughout the Eastern Strait was predominantly characterized as medium risk. But when we use the expert scores, those became characterized as high risk. So just one notable change there. And then on the eelgrass side, kind of the opposite was also true in some cases. Areas of North Puget Sound and the Saratoga and Whidbey basins switched from being characterized as high risk under the equal scores version of the risk assessment to being medium risk under the expert scores version of the model. We can also see the change in the relative influence of each of the threat layers in the equal versus expert versions of the model. So here, red cells are indicating where the use of the expert scores increased the relative contribution of that threat compared to the equal scores version. And then blue indicates where the expert scores decreased the contribution of that threat to total risk. So some interesting changes there. And while we see that pixel by pixel, the expert scores influenced our estimation of risk, and that individual threats kind of increased or decreased their contribution in response to those scores, actually at a sub-regional scale, the patterns of high and low risk subregions remained approximately the same. So the expert scores tended to influence our calculation of risk at scales smaller than the subregional scale. We can also dive into the data by zooming in on a particular subregion and looking at how total risk and the risk from individual threats differs across the subregion. And this is a demonstration of how we think the web tool, which we're going to demo here in a little bit, can be used by an individual. So here I've zoomed in on kelp risk in the San Juan Islands. And in the upper left corner here, outlined is in red, is the total risk. Again, the results that you have already been seeing, but we've zoomed in on the San Juan Islands. And then what's shown in the additional panels is risk from specifically the top 5 contributing threats in the San Juan Islands subregion. So for total risk, in the upper left, we see that risk tended to be highest in the San Juan Islands in kind of the center of the subregion, almost along a transect from the southwest corner to the northeast. And there were lower risk areas such as the small islands on the north portion of that subregion. High nutrients was the highest ranked, the highest ranked threat based on contribution to total risk in this subregion. And high nutrients risk was more prevalent in the southwest portion of this subregion, whereas low nutrients was kind of a widespread risk distributed across the subregion. Vessel traffic was fairly low risk inside this subregion compared to others, but it's still the 3rd highest risk in the San Juan Islands based on relative contribution. And it's important to recall that this data set only captures vessels using AIS transponders, which tend to be kind of the larger watercraft. So we're not necessarily capturing small pleasure craft or privately owned boats in this. Temperature risk was greater in the northeast portion of the subregion, and then river flow risk was highest in the center of the subregion. But it's also important to note that the Canadian rivers, such as the Fraser River, were not included in our river flows and river nutrient loads data sets. But those were incorporated into the Salish Sea model output. So those would be captured in our estimation of high nutrients, low nutrients, and temperature, but not in the river flow data set. This is the same figure, but for eelgrass. So total risk to eelgrass is distributed across the subregion, but with distinct hotspots. Couple of examples would be Westcott Bay and San Juan Island, Fisherman Bay on Lopez, and then there's kind of a lower risk area on the southern end of San Juan Island, around Cattle Point. Shoreline armor risk is distributed across the subregion, but with distinct hotspots. And then similarly to kelp, temperature risk is greater in the northern and kind of northeast portion of the subregion, and high risk from high nutrients was predominantly in the southwest portion of the region. And then vessel traffic, again, only from larger vessels with AIS transponders, had a few hotspots kind of in the center, and impervious surface coverage risk was highest also in the center of the subregion. So this type of detailed assessment is what we hope folks will be able to do with the web tool, and that kind of within the overarching context of local priorities and local needs, that the tool that allows you to investigate these results at this level can help to support marine vegetation management. At a high level, to our knowledge, this project represents the first attempts in Puget Sound to rate threats to kelp, to perform a habitat risk assessment, and to synthesize all available threat data for marine vegetation into a common framework. And I really undersold that portion of the project, which was the kind of data collection, data synthesis portion when I discussed it earlier, but that represented the lion's share of the work on this project. And so we're really pleased to have been able to do that successfully and bring these data sets together into a common framework. Overall, we found that risk to eelgrass and kelp in Puget Sound is spatially diverse. And I just want to note that low risk areas should not be considered safe, but they may be places where our approach to research monitoring and management is a little bit different. One idea for future work is that regions with similar risk profiles, but with different trends in marine vegetation, such as one that's increasing and one that's decreasing, or one that's stable and one that's decreasing, could be compared to elucidate possible causes for those differing trends despite having similar risk profiles. And I just want to mention that I think that this spatial risk assessment at a system-wide scale complements some of the really fine ongoing work to identify drivers and management interventions at finer scales, and that approaching the problem of marine vegetation persistence from multiple scales will result in better outcomes altogether. And just a couple notes on where we're headed from here before we launch into the Webtool demonstration is that we have manuscripts in preparation. As Wendell mentioned, the Kelp threat rating manuscript, as well as a manuscript on the risk assessment. And then we'll be finalizing and officially launching the Webtool, although we're going to give you all a preview of that today. And then we expect to make the habitat and threat layer input layers, as well as the invest results files and those spatial data layers available through archives at the UW libraries. So I'm happy to share those once they're available. And then updates or refinements to the risk assessment are certainly possible. I'm sure you're thinking about your local setting and specific data sets that you have available at a finer scale, which might be more well suited to identifying risk hotspots. And all of that is certainly possible, but may require additional funding, just kind of depending on the level of investment. So please reach out to me with your ideas, and I'm happy to explore what that might look like. Okay, so now I'd like to share with you what we have for this web tool, which allows you to explore the results of the risk assessment. And I'm going to kind of orient you to what that looks like in the tool, and then ask you to take some time to do your own investigation. And then we will have lots of time, hopefully, left to have some more discussion about the overarching results and kind of applications for this web tool. So once we give you the links to the web tool, first thing to note is that you may need to create a free account. So you may have to kind of just enter your name and email address, but that should just be about it. And then you'll be able to access the web tool. There'll be a splash screen that comes up with just some high level information, and you can read through that quickly and then click explore to get into the web tool itself. Once you do, what you'll see is two panels side by side. The left panel shows cumulative risk for either eelgrass or kelp, depending on which link you open. And the right panel allows you to click through risk from individual threats. So for example, if we wanted to see more detail on industrial land use, you would click on the little eyeball symbol next to industrial land use, and that brings up a side-by-side layer where you're looking at risk from industrial use on the right and total risk on the left. And just to note that it is possible to view multiple threats at a time, but you are only seeing the topmost threat when you look at the screen. So I would encourage you to be in the habit of turning one off at the same time that you turn another one on, so that you know for certain which threat layer you're looking at. Okay, so and then sorry, if you click on an individual pixel, so if you zoom in and you click on an individual pixel, that will bring up additional information, including information about the contribution of each threat layer to total risk in that cell. So you'll kind of see a pie chart with percentages, and you'll also see a table with numerical information. You can use your mouse to zoom in and scroll around. If you have a little scroll wheel on your mouse, you can use that for zooming in and out, or you can double click to zoom in on the map. And you should also be able to pan around anywhere you like. So my assignment to you all, and let's take about 8 minutes to do this. You can also grab a bio break if you need to in this time, but I believe Marielle has put the links to both the eelgrass and kelp web tools into the chat, or if she hasn't, she will do that momentarily. Please choose one of the two to look at that you're interested in and open up that web tool. I encourage you to navigate to the Eastern Strait portion, Eastern Strait subregion, around the Port Angeles and Squim areas, and look at the top threats, which I've listed here. So industrial use, impervious surface, river flow, river pulse, high nutrients if you're kelp, or shoreline armor if you're eelgrass. Those are the top 5 threats to eelgrass and kelp in the Eastern Strait subregion. So let's take some time and do that on our own, and then we'll come back together and talk about what you've seen, as well as any other high-level discussion or questions you all have. Thanks, and see you in about 5 more minutes. go ahead and take about another 90 seconds or so, and then we'll come back. Okay. So I guess I'd like to hear from you all about your experience in looking through the web tool and how easy you found it to identify some of the patterns between total risk and risk from individual threat layers. So let's start with anyone who looked at Kelp in the Eastern Strait. And if you want to volunteer to raise your hand or put something in the chat for what you noticed on kelp risk and risk from individual threats. Yeah, go ahead, Tom.
Go for it, Tom.
Oh, sorry, Tom. Can you unmute yourself again?
How's that?
Perfect. Thank you.
Okay. What an amazing tool. My question was, how can we make this more of a living document kind of a thing where you could have users and other people help you input better, more different data into it? Is that kind of built into this thing?
Yeah, it's not exactly seamless to do that. But I love that idea, and I think it's worth exploring how to make that a little bit more less kind of manual way to do that. If someone says, I have this data set, and I want to swap it out for that data set, if there was kind of an easier way to be able to do that. I mean, the way that I would say to do it now is, sounds good, send me that data set and I'll stick it in and I'll rerun invest, right? But
Right.
depending on the level of time investment to do that, that might be a fairly slow process. So yeah, I mean,
It's such a great way to approach this thing. And how can we take advantage of the communal knowledge, if you will?
yeah.
And along those lines, I see a suggestion in the chat that in a similar model with coral reefs, that they allowed users to adjust sliders for the weight of each contributing stressor, so that users could kind of reflect that local knowledge. I'm not sure if that's possible with Invest, but just I love the brainstorming of ways to move towards that.
Yeah, that's a really interesting idea. I mean, at present, Invest is a desktop tool. So it is not one that is embedded in a website that you can necessarily change those parameters in real time. But it would be really cool to move to that place. And I could imagine a a scenario where we might be able to get there. I mean, it's a fairly lightweight, straightforward calculation. And if you could have a web-based format where then you point it to a file on your machine that has the relevant data layers, then I could imagine a situation that has kind of toggles and options for changing different parameters. Yeah, really interesting idea. And I'd love to see the coral example. So I'll look for, hopefully there's a link to that in the chat perhaps, and I look forward to seeing that. Other thoughts on actually digging into the tool and seeing what's there? As I mentioned, this is not the final version of the web tool, and so we are interested in hearing from you what your experience is in trying to use it so that we can iterate on that and make a kind of better final version. And not all things will probably be possible in the short term, but any comments are welcome, and we'll certainly consider those. Yeah, Laura.
Hi, Caitlin, I'll bite. Thanks for this talk and thanks for building this tool. And please feel free to tell me I asked a question that the tool wasn't built for as I was playing around in it. But I sort of approached it, and I looked at an area with high risk in the total score. So I kind of zoomed in on the Dungeness bit, and then was toggling on and off the threats, trying to see, what was really driving that yellow that you see in the total score. And and as I did that, I thought, well, it would be really neat if you could toggle them on compoundingly and see the spots shift as you turn things on, in compound, right? So you look at industrial use first, and then as you add high nutrients, you see the parcels shift in real time. And that's probably really hard to do. And again, feel free to tell me that's not what it was built for, but that's kind of where my mind was going as I played around in it.
That's cool. Yeah, that's a really interesting idea. I would leave it to our GIS person, Kevin, to comment on whether that type of functionality where it adds as you add additional layers is possible. I don't know, Kevin, if you have a quick answer, but
anything is possible with enough funding.
excellent answer, Kevin.
As it stands out of the box, unfortunately,
not a super easy task.
It's not a super easy task out of the box, but given time and resources, hopefully we could bring that idea to light.
Yeah, that's a cool idea.
That said, like Caitlin alluded to, this is, a rough draft of what'll be the final web tool, and overall just kind of a first step in what is hopefully a very long journey to a very useful analysis and tool that can help us all sound-wide.
Yeah, thanks, Kevin. Beth, I see your hand.
Yeah. Just back on that other page, and it's related to Laura's observation. Maybe you could kind of talk through what the model is doing. I got behind as well, just pulling up the website, but now that I'm seeing them side by side, and none of them are rated as high individually, but cumulatively they are rated as high. And so is the model assigning a numeric value and then adding those together to come up with this cumulative value and then expressing that? And I guess it just makes me ask a few more questions about, I know this area pretty well. I actually live up in this area. It makes me wonder about drift and other water flow patterns that might be contributing to this from those individual factors.
Yeah, good questions. Okay, so I heard a few, which is how is the risk from the individual threats being incorporated into total risk, and then kind of
Yeah.
also how does that then get assigned to low, medium, high?
Yeah. I mean, you would expect, I would expect one of those individually to be high for it to be elevated to a high, but it sounds like that's not the way the model works. Sounds like it's adding up them and then cumulatively expressing that.
Yeah. So the risk from each individual threat is then summed to a total risk value.
Okay.
And then that gets categorized basically using quantiles into, well, like the lowest third of those values is characterized as low risk. Or if you're actually 0, then that's no risk, right? But the lowest third is low risk, the medium third is, the middle third is medium risk, and the upper third is high risk. But that's across the sound. So sorry, let me, across Puget Sound. So some of these areas are high risk, you know, relative to the full distribution of risk values across all of Puget Sound.
Okay. Got it.
That's true for these threat layers too, right? So the basically the color palette that's displaying in the figures I'm showing you here, but also on the web tool, are relative across all of Puget Sound. So you may not see areas in Eastern Strait lighting up necessarily, you know, you don't see lots of yellow, for example, for high nutrients, but that's because nutrients are higher somewhere else. But you can end up at high total risk by either having a lot of low level risks, maybe like all 16 of the threat layers are present to some degree, but not necessarily the highest, but you just have a lot of overlapping threats. That could get you to high risk.
Okay.
Or another way you can arrive at high risk is by having a few really bad threats.
Okay.
If
That makes sense. It's a sum.
Yeah, it's a sum.
Yeah, it's a degree and a sum. Okay. Okay, thanks. Appreciate that. That
Yeah,
helps.
no, great question. Thank you.
Yeah, I think there's lots of good suggestions in the chat too about the thinking about the interpretation of that and the framing, which will be really helpful. In this theme, there is a question about a distinction between strictly additive versus non-linear cumulative effects.
Yeah, absolutely. Very good point. I mean, we know that a lot of these threats, especially the interactions between them, will be nonlinear. That there will be thresholds, there will be complex interactions, there will be compounding effects, but there may also be antagonistic effects, right? So this framework is not particularly well suited to tease apart those kind of more complex interactions or nonlinear effects. So that's certainly a shortcoming. But in many ways, right, it's meant to be a qualitative assessment rather than a quantitative one. So I still think we can say qualitatively these risks, these areas are more high risk than other areas. It's, you know, both relative and qualitative, although there are like equations and numbers that underlie the values. But really
Thanks,
excellent
Caitlin. I
point.
appreciate that context.
Yeah.
And so one of the themes that keeps coming up both in questions and suggestions is really wanting to understand when folks have better data at a kind of sub-region level, what opportunities exist for that.
Yeah, really good point. To Tom's question or suggestion earlier that it be more streamlined process, I think that would be a really excellent goal to move towards. In the short term, I think we'd have to consider those kind of on a case by case basis. And I'll provide maybe two contrasting examples. Like One is that first of all, that you have GIS skills, in which case I can share with you all of the spatial data layers and the information that we have. Invest, the habitat risk assessment model is open source and free to download. It's a free software that you can download from the Natural Capital Project. So very easily I could set you up and say, here's the files that I have, replace any of them or some portion of any of them with the information, the better information that you have, and you're good to go. But that requires some GIS capabilities. If you don't have GIS capabilities, but you know about data sets that are available, also come, talk to me and we can figure out a way to support that too. I mean, fairly simple substitutions don't really require too much of our time. And so those things may be quite possible. And it may be a case where we, instead of doing the whole Puget Sound, we're just drilling down on a smaller area. This framework is adaptable across a wide range of spatial extents. And so that's fairly possible. But yeah, I don't have like a general rule. It's kind of on a case-by-case basis, I think, at this point, but would love to move towards a more integrated and kind of streamlined process that would allow people to do this on their own through just a web-based platform. But in the short term, that is unlikely to happen.
Appreciate that context in terms of timelines, always helpful there. We've gotten a lot of really great suggestions about kind of additional threats to consider, ranging from invasive species to recreation to crab pot density to some of the things around fetch or wave exposure. And I think that ties into what's possible from a timing perspective for each of those data sets, and the goal of making all of this available such that if people want to layer that on themselves and have additional capacity, that's one pathway. But we also have some questions that are a little bit more about understanding the current layers that are in there. So I wanted to just quickly come back to those. One is around temperature and whether you're looking at means or time above temperature thresholds, i.e. extremes.
Yeah, good question. I'll drop into the chat again the kind of list of data layers and data sources, but for temperature and for any of really any of the continuous data, either observations or modeled data, we didn't presume any sort of threshold or specific value to be stressful or not stressful. We simply divided the data into quantiles. So 4 equal segments of data, of the observed data. So for temperature, this is modeled data from the Salish Sea model. We divided all of the data into 4 segments. The lowest quarter was associated with a low intensity score. The middle 2 quarters, so kind of the middle 50th percentile of data got a moderate intensity score, and the upper quantile of data got a high intensity score. We found we decided on that approach because it was adaptable. It was one that we could use across all of the continuous data versus trying to prescribe specific temperature thresholds and then specific salinity thresholds and specific nutrient thresholds. And in some cases, we know those values fairly well, but in lots of cases, we don't know those values very well. So we found that this approach, this quantile approach, was kind of was applicable regardless of which threat we were thinking about. But it is certainly possible to define and prescribe those thresholds more specifically and redo the analysis that way. We just didn't feel like we could justify that at a Puget Sound wide scale. Is there another
Great.
part of
I
that question,
appreciate
Mario?
that context, Caitlin. No, I think that was good. Similarly, in terms of just kind of clarification, was whether or not water turbidity is incorporated into the river associated parameters.
Yeah, we didn't have a good data set for water clarity, one that was available at a Puget Sound wide scale, kind of with the right spatial coverage that we were looking for. And this is definitely I'd say like a blind spot in our analysis, because we know that water clarity is really important for both eelgrass and kelp. But I would say that some of the threat layers we did compile provide a proxy for water clarity. So locations near river mouths are likely to have more sediment load and just more particulate matter. And so our river flow and river loads data sets can serve as a proxy for reduced water clarity or light availability. Also, vessel traffic might be associated with increased resuspension of bed material and therefore reduced light availability. So sediment kind of light stress could be associated with the vessel traffic intensity layer that we compiled as well. And when we used the expert scores, we made those types of judgment calls, like where is sediment stress likely to be associated with the different threat layers. And so the sediment or water clarity scores were then associated in an additive fashion with that threat layer. So we tried to capture where the threat layers we compiled were proxies for multiple potential stressors.
Great, thanks, Caitlin. I'll do one more question and then just any closing thoughts you have, which is just around the possibility long-term of running the model to look not just at current distribution of floating kelp, but also historical distribution, and how that potentially aligns with some of these stressors.
Yeah, that's been in the back of my mind too. And I think that's a really interesting idea. If we have spatial data layers, and I think in the case of kelp, we probably do, but I'm not sure about eelgrass. But so if we have spatial data layers describing the, a past historical extent of kelp, we could simply switch the habitat layer in the invest model to use that historical extent rather than current extent. Then I guess the question is, do we think that the threat layers that we compiled still apply if we're thinking about kelp extent in the 1950s, for example? So we'd have to reconsider whether going back and revising some of the threat layers is needed as well. But maybe just at a first pass would be to run the existing threat layers with a historical extent, and just see what it says about high risk areas. And we know where we've lost kelp, for example, and so do those tend to be more high risk areas as well. So I could imagine kind of a first level approach to that, which would be very simple and just running invest as it currently stands, but with a historical kelp distribution extent. And maybe that's the first step, and just kind of see what that says.
Awesome, thank you, Caitlin. And I know there was lots of great suggestions and questions in the chat. If we didn't get to the specifics of it, we will definitely follow up with you offline. But know that we're processing it all and building on it, and we'll think about what next steps come from there.
Thank you all so much. Yeah, thank you all so much. It's really exciting to have such a big group for this today. Please keep an eye out on the website for more information and kind of the official launch of the Webtool. And my email's here on the screen. Please reach out if you have other suggestions or ideas for future work or refinements to the existing project as is. So thanks, everyone.